It's a real pleasure to have Professor Stefano Liberati with us today at this virtual RRI colloquium. He has many honors to his credit, but I will not talk about them here. Instead, I'll talk about the contributions he's made to physics, in particular to two areas of physics, one of which he'll talk about today, which is analog gravity. But the other area is that of quantum gravity phenomenology, which may be something that most people don't realize is there, is an actual field. And Stefano, along with Ted Jacobson and David Mattingly, have done some stellar work on it. In fact, I would say Stefano's work is sort of the gold standard in the field, basically asking the question whether there can be violations of Lorentz invariance from, some quantum gravity theory, some higher derivative theory of gravity. And basically these are studied using modified dispersion relations. And they have found very stringent bounds on these. And like I said, it's sort of the gold standard in the field. In addition, he's also made major contributions to analog gravity, which is basically the study of trying to understand whether you can simulate things like Hawking radiation in the lab using condensed matter systems or superfluids and so on and so forth. And Stefano was perhaps the first to suggest that these things could be studied very effectively in Bose-Einstein condensates. And so it's a great pleasure to have him here today to talk about this, to tell us more about analog gravity. And before I hand over the thing, I would like to say that Stefano is a very nice person to know. And I hope one day he can visit RRI, and I think he'll enjoy the atmosphere here as well very much. But for now, we're happy that he could make it for this virtual colloquium. So over to you, Stefano.
Thank you, Sumati. Thank you for the nice words. Okay, so today I want to bring you to a kind of trip in describing some recent development in analog gravity. Let me try first of all. Let me try first of all to give you some motivation of why people got interested in analog gravity. See, general relativity nowadays is very well understood. I mean, we use general relativity every day in our mobile phone when we look for a place with a map application. Basically, we are using the GPS system, and the GPS system needs to take into account the correction due to both special and general relativity in order to be precise. It is an everyday experience, in spite of the fact that most of us do not realize it. General relativity. Nonetheless, the same very theory that we use for this mundane application has very severe consequences in some situations. In particular, general relativity predicts singularities, which is quite weird because you see, recently we had the Nobel Prize by Roger Penrose, and I would say that one of the main reasons behind the Nobel Prize are, and rightly so, the singularity theorem by Penrose. Basically, these are theorems. The main theorem is the one regarding concerning stellar collapse, which are proving with topological methods very efficiently, very simply. His first paper is a 3 pages PRL that general relativity under standard condition for matter predicts its own demise, predicts singularities, which are places where basically general relativity is not predicted. At the same time, we have several weird occurrences in standard general relativity. We have critical phenomena in gravitational collapse. We have that black holes behave as thermodynamical objects. We have that basically there is a kind of duality between heterodynamics and general relativity, in the sense that if you project the Einstein equation on some spatial surfaces, basically what you get is a Navier-Stokes equation. So there are a series of weird aspects of general relativity that make you think that this theory definitely is not the fundamental theory of gravity, and that there might be something deep beneath it. Today, I will show you how analog gravity can shed some light on two very puzzling aspects of general relativity. One is horizon thermodynamics, the thermal behavior of black holes. And the other one is the fact that we can explain the dynamics of our universe, but with a very weird composition. In particularly, most of the energy content of our universe nowadays is supposed to be in the form of what is called dark energy. It's a kind of tension that pushes to expand our universe. It doesn't behave like standard matter that would tell gravity to basically contract the universe. Instead, this dark energy tells the universe to expand faster and faster. And we don't know what it is. And even on this, analog gravity as a toy model of an emergent system where space-time is emergent from a more fundamental structure, the atomic one, can provide a toy model, a kind of a test bed for some of the ideas of how to resolve these problems. Now, before we move on, some of the first things I want to discuss is basically what is a black hole. I've been told that not all of you are working in gravity. And of course, black holes are now a science fiction, are very popular in pop culture. But what is really a black hole sometimes is not completely understood. So I would like to basically to describe a black hole, starting exactly with an analogy. So normally, if this one on the left is the Monticello Dam in Napa County in California, this is basically a drain, a huge drain hole, and then you see the hydrodynamic flow of the water goes radially inside this drain. What is happening here? If you think about a sonar that is thrown inside this drain, if you have a region where the flow becomes supersonic, what you have is that the sound waves emitted by the sonar are basically forced to go only in one direction. Basically, if the flow is less than the speed of sound, the sound wave, here I have time and space, and I have suppressed one spatial direction. Basically, you have what is called the sound cone. Now, if the flow goes in this direction faster and faster, if you are in a supersonic region, you see even the ray that normally would go in the negative x direction now is forced to go in the positive x direction. Now, if you think of it again, if you have an original region, this is supposed to be an area because I've suppressed one spatial dimension. Then what is happening? That an area is connected, if you are in a region of subsonic flow, to a larger area. You can basically causally connect by sound. You can send signal in a larger area. They expand. Now, if you have a region where you are in a sonic flow, the sound waves that are supposed to go outside before, now they basically stay at the same point. So the area that is connected after some time is the same size. But if you are here in this region, given the tilting of the sound cone, the area that is connected at a later times is smaller than the area that was connected before. So you are, is what we say, in a trapped region. If you are starting here, you cannot go in a larger region in the future. You are forced to be in a smaller and smaller region. Now, this analogy is exactly mutatis mutandis. What you have to do is that you have to replace the fluid flow with space-time, the sound cones with light cones. And basically what is happening is that the light cones, as you move into a black hole, they tilt in such a way that even the would-be outgoing rays are forced to stay in a given region. This trapped region is the black hole. So you see, there is a kind of qualitative analysis that we have used to explain what is a black hole. A black hole explains also why it's not the appropriate analogy of throwing a ball and the escape velocity being faster than the speed of light, because it's not that the light cannot do like the ball, it cannot slow down and come back. It's simply tilted, it moves always at the speed of light, but even the light that tends to go outside past this region, the event horizon, basically cannot reach infinity. So black holes are a crucial role in general relativity because they are the purest object. They are purely gravitational objects. And for this reason, they have a special role in general relativity because they are basically the hydrogen atom of gravity. the interesting point, of course, is that we now know that there are many black holes in the sky, and these black holes have a huge dimension, huge sizes. They can reach sizes which are well beyond the size of our solar system. This year is a 40 billion sun black hole comparison with our solar system. One aspect that made black holes so interesting is Hawking radiation. You see, black holes are extreme objects where something incredible can happen. If you take a black hole, you would expect that it's completely cold because nothing can escape from a black hole. But of course, there is quantum field theory we know now. There is quantum mechanics. So in quantum field theory, in any moment from the vacuum are produced and destroyed pairs of particles. What is happening is that close to the horizon of a black hole, you have two ingredients. One, you can have a very large tidal forces. As you know, gravity is basically encoded in tidal forces. Tidal forces at the horizon, they scale like 1/m². So basically what is happening is that the smaller the black hole, the stronger are the tidal forces. And what they do, these tidal forces, they can break these virtual pairs. Now, normally, energy has to be conserved if there is no time dependence in the system. So what is happening is that if the energy of the vacuum is zero initially, once you break the pairs, one pair needs to have a negative energy and the other needs to have a positive energy. This can happen close to a black hole because you can throw immediately the object by quantum tunneling with negative energy inside the black hole and reduce the mass of the black hole, and having the partner, what we call the Hawking quanta, escape to infinity. So black hole, via this mechanism, produce a steady thermal flux. Of course, this thermal flux is very difficult to see in
Stefano,
nature.
can I ask a question?
Yes.
Yeah. So what forbids that the negative energy comes out and the positive energy goes inside the black hole?
Because you cannot have a negative energy state outside. The point is that what is happening inside a black hole? Okay, what is energy? Energy is defined normally with the Nether theorem. So you need to have invariance under time translation. If you have a geometry which is stationary, that means that is invariant. The metric elements are invariant under time. They do not depend on time. You have a preferred vector, which is called a Killing vector, which is associated to invariance under time translation. The energy is defined by projecting the force momentum of the particle on this vector. Now, outside of the, basically you cannot have negative energy states outside, but inside the black hole, what is happening is that the space-time is so twisted that this vector basically becomes a space vector. And what is happening is that it means that you can have a negative energy state and you can interpret it inside as a momentum, basically. You see, as a negative momentum because the vector exchange behavior. So that is the reason why you can, is important that this particle breaking appears close to the horizon, because you need to throw this object immediately beyond the horizon by quantum tunneling, by uncertainty principle. This is allowed in such a way that it can exist, this particle, okay? Is in fact, the region behind the horizon is called an ergo region. An ergo region for a rotating black hole can happen even outside of the horizon, and there you can have a particle production even classically, because you can mine these negative energy states, and this is called the Penrose process, which in the field theory formulation becomes superradiance. But this is a completely different story. So the point I wanted to make is that, you see, Hawking radiation is very faint. It's very difficult to see. Basically, you need a microscopic black hole to be hot enough to be hotter than the cosmic microwave background. So it is very hard that we are going to see any time Hawking radiation in astrophysics. However, not all the hopes are out, because sometimes the analogy that we use to define a black hole can be pushed beyond, can be made in a mathematical analogy. So let me give you the paradigmatic example. This was basically seen by Urru in 1981, albeit it was a rediscovery of something that surfaced in the literature many times. So basically the idea is very simple. Start with a continuity in the Euler equation and now make the assumption that your fluid is inviscous and it is irrotational. That means that the velocity can be written as the gradient of a scalar. The scalar is called the velocity potential, and has a barotropic equation of state. Then if you consider a small perturbation on the background, you can linearize these two equations and put them together and to get the second order field equation. The second order field equation can be recast as a Klein-Gordon equation, the equation for the propagation of waves, for perturbation in the velocity potential in the scalar that we have defined here. So what is happening is that you have a generic form of the metric, this is called the acoustic metric, that tells you that basically waves on the system propagates like a scalar fields on a curved background. And that was the basic realization. Then Unruh basically said, well, this metric has an expression which is complicated enough to allow me to simulate some interesting geometry like Friedmann-Robertson-Walker or black holes. And then I can, in principle, if I have a system where I can quantize this wave, I can talk about phonons, then I can even simulate Hawking radiation. Just one caveat, that this can be done even in relativistic fluids. In that case, you will have a more complex structure of the geometry that can be useful for other applications. So there are many models of analog gravity that have been developed over time. I will focus here mainly on Bose-Einstein condensate, which are probably the most versatile and the one that has been recently explored better from an experimental point of view. As I was saying, most of the literature on analog gravity has been focusing on using this system as an analog system of classical or quantum field theory on a curved spacetime. What we will see today is that there is a possibility to push beyond this analogy and try to learn some lessons from the fact that you have a toy model where spacetime is emergent from fundamental discrete objects, the atoms. So let's see analog gravity in Bose-Einstein condensate. The basic idea with which you recover basically analog gravity in Bose-Einstein condensate is to use the fact that a Bose-Einstein condensate in some limit is basically superfluid. That is the upshot. So the way you see that is very simple. You start basically with your nonlinear Schrödinger equation, which is the equation for a non-relativistic Bose-Einstein condensate, where this is the operator that is describing the creation of and destruction of atoms. And then you basically do a mean field approximation that is a legitimate approximation when you have a dilute condensate of weakly interacting atoms. And then what you do is that you basically express, basically you have a classical wave function of the condensate, because this is the expectation value of the condensate state, the ground state for most of the atoms. And then you describe a quantum excitation above the state. Notably, here you have a different definition. Of course, they are inequivalent, the ground state for the atoms and the ground state for the excitation. That is something we will have to keep it into account later on. Now, what you do is that you insert this constant in your nonlinear Schrödinger equation, and basically you have an equation for the excitation, which is normally called the Bogoliubov-de-Gennes equation. And this, once you neglect these terms, which are related basically to the back reaction of the quantum excitation, is what is called the Gross-Pitaevsky equation. These are the basically fundamental equation for analyzing Bose-Einstein condensate in this Bogoliubov approximation. Now, what you can do is that basically you can do a Bogoliubov transformation, because what you can do is basically diagonalize your Hamiltonian, or in another way, you can go in a different basis in such a way that basically you got to some sort of hydrodynamic variables. These N1 and θ1 are playing the role that in the acoustic analog I told you before, where the perturbation in the density and the velocity potential. And what you get then is a couple of equations that again you can linearize. So I'm working now on this equation and I'm doing these ansatz. And what you get, you follow basically the same route as before, with the difference that now you have this quantum potential, which is a differential operator. Now, let me neglect this for a moment. I say, okay, this is suppressed by h square. And if I consider perturbation waves, which are long wavelength, basically this is an operator that is negligible. So what I can do is that if I neglect that, I get again to an equation for the perturbation in the velocity potential, which is the phase, the perturbation in the phase of the condensate, which is again of the form of a wave equation on a curved background. And again, you see, we find again the acoustic geometry. But of course, you are not obliged to do that. You can decide to not neglect that differential operator, and then you can do an equal approximation. You can consider high frequency. And then what is happening is that you see that the dispersion relation gets more complicated. If you neglect the term, you don't have this k to the fourth term. You have only this omega square equals sound square k square, which is basically a relativistic dispersion relation with a Lorentz group determined by the speed of sound. But if you go beyond, by not neglecting the quantum potential, you have this correction, which is telling you that you have a UV Lorentz breaking in this system. So what we are seeing,
Sorry, can I just interrupt? Something that I seem to have missed is understanding what the Bogoliubov transformation is between. What is
basically it's like this is the equivalent of the Madelung. It's called quantum Madelung representation. What this is equivalent to rewrite. Normally, for example, you can get the same result by neglecting this and rewriting the psi as square root of rho e to the I theta. And that is the Madelung representation. It's a way basically to go. It's like when in the Schrödinger equation, you go to hydrodynamic variables, right? Here is the same transformation for these quantum excitations, basically. Is already taking into account this fact. And you can see it as a Bogoliubov transformation that send you basically the Hamiltonian in a basis in which it can be written as A cross A plus 1F, basically, okay? So it's basically diagonalizing your Hamiltonian for you. And this is the way in which you identify quasi-particles on the condensate, which are basically the collective excitation that propagates on the background.
So is it sort of similar to how we have coherent states and then the standard vacuum and the coherent state, and they're two different bases in which you can, is that similar to this? Or
well, this approximation, for example, the Gross-Pitayevsky equation, this part is exact when you work in a coherent state. In that case, you don't have these extra terms. And here you are, what you're doing is that now you're looking at the quantum excitation over this coherent state, and you want to propose to change basis in such a way that you can describe them as particles. You want to have a creation and destruction operator for these objects, and though you have basically this as particle propagating on this background. So these are particle coherent excitation over a coherent state. You can see them in this way.
Thanks.
So now, so you see, when you neglect that extra term, you have basically a relativistic physics. You recover basically a field on a curved space-time. But if you don't neglect it, you have this UV Lorentz breaking. You have this UV Lorentz breaking. And sorry, but they're keeping calling me, of course, in the wrong moment. So, and you have a UV Lorentz breaking, and that is interesting because this is, for example, was a motivation for me also to go to quantum gravity phenomenology. Can we test this modified dispersion relation in real life? Because this would be a possible signature of a way to introduce discreteness in the space-time. The alternative way, if you don't want to introduce discreteness, is to have not an extra scale breaking Lorentz invariance in this Klein-Gordon, but to introduce a function of your D'Alembert instead of having a D'Alembert, and that will lead to non-locality. And that is what's happening when you have the continuous limit, basically, of a discrete system with built-in Lorentz invariants like causal sets. But that is another story. So that's all I want to say is that this is a system where you can simulate quantum field theory in a curved space-time because it's a quantum system. So quasi-particle can be quantized, canonical quantization works, but at the same time, at high frequency, predicts Lorentz breaking. And that is a very interesting feature as well, we will see in a second. So the natural next step is to simulate black holes in this system. And how you can do that, these were early ideas, like having traps, toroidal traps, where you have basically narrow places like naval nozzles, where the flow accelerated, becomes supersonic, and then you need to slow it down by another throat where it becomes again subsonic, and so you have a black hole and white hole horizon. The white hole, you can think of it as the time reversal of a black hole. And but in real life, they were finally made with two tricks. The one that is most effective was the one that was considered more difficult to do, which is a waterfall. Basically, you have a potential swiping through.
Stefano, can I ask a question?
Yeah.
Yeah. So when you say white hole, it means basically that nothing goes inside, is it?
Exactly. It's the time reversal of a black hole. Basically, imagine a flow. You can do it in your sink.
Can I think of it like a spherical mirror or something like that?
No, take a flat dish, put it under your sink in the kitchen, and have a flow, a column of water coming down. You will see that a column of water draws a circle. Now try to, with some stick, to send waves inside the circle. They will not penetrate the circle. That is the circle because it's the horizon for gravity waves. You know, they're surface waves. In a shallow basin, have a speed which goes like basically square root of GH. The H there is very small. So what is happening is that the flow is flowing outside so fast that basically no wave can penetrate inside. That is a white hole horizon. Mm-hmm. So it's exactly the time reversal of a black hole horizon from this point of view. And it's even easier to do sometimes in hydrodynamics.
Thank you.
So I was coming back to the fact how you generate black holes. Basically, you generate a waterfall by sweeping a step potential through a one-dimensional Bose-Einstein, effectively one-dimensional Bose-Einstein condensate. And basically, the velocity becomes supersonic at some point, and so you have an horizon. Another possibility is to change the scattering length of the condensate. We change the speed of sound of the condensate in a given region by using a trick which is called a flashback resonance. For people working in cold atoms, basically, you change the scattering length with a magnetic field. How we can use this machinery? Well, the first problem I want to discuss is the so-called Transplanting problem. The Transplanting problem is an interesting problem because it's basically due to the fact that if you break the pairs close to the horizon, the Hawking quanta that has to escape, it has basically to climb up a very steep gravitational potential. So it loses a lot of energy. Actually, initially, it loses exponentially energy. So if you have a finite energy...
Sorry, Stefano, just again. See this, so when you say this white hole, so do you mean that the outside of a white hole will be like inside of a black hole?
The outside, no, it won't be, there won't be outside of the white hole a singularity. It means simply that the space-time is twisted in such a way that the light cones are pointing at the white hole horizon this way, outside, instead of inside. So if you travel inside the light cone, you are forced to get out of the white hole, but the singularity will still be in the interior. So you are forced to escape from the singularity instead of falling inside. Okay, so if that is bad, because if you could see a white hole, then you could have rays that in principle could leave the singularity, right?
Okay.
So talking about the energy to climb up, to escape from nearby the black hole is huge. So what is happening is that if I take a finite Hawking quanta here and I trace it back close to the horizon, it gets exponentially blue shifted. So sooner or later I encounter Planckian energy. These Planckian energy are against the idea that you want to work with a field on a fixed classical geometrical background, because basically quantum energy, a Planckian energy, you would expect that you need to go for a quantum description of space-time as well. So this is the expression for the Hawking temperature in an acoustic black hole, which is, if the speed of sound is constant, is basically the variation of the speed of the flow in the normal direction to the horizon. Now, this was the main motivation. So what happens in an acoustic system? Well, you see, we saw that at very high frequency, you have a breakdown of Lorentz invariance. And depending on the analog system, it can be superluminal with a plus or subluminal with a minus. So in the plus, for example, is the Bose-Einstein condensate. So what is happening is that in one case, if it is subluminal, if you trace back in time, you will see that the Hawking quanta basically reverse the sign of the group velocity before of reaching Planckian energy and comes basically from the past. While if you have something that is superluminal, it again change behavior before of reaching Planckian energy. Now you may say, well, but that how do you know that Hawking radiation is robust against this different behavior close to the horizon? Basically, how it can be robust against Lorentz breaking? And you see, the lessons that we learn by direct computation is that, of course, it's much more complicated. You have here 4 different modes that you have to analyze for solution and so on. But you see, the crucial point what it is that is as long as the scale of Lorentz breaking, what they call kappa here, or most something parametric related to it more correctly, is very different from the scale of the Hawking radiation, which is set by the surface gravity that I've just defined before, then if there is this separation of scale, then you know that Hawking radiation is unaffected, which intuitively is okay, no? Because basically what it's telling you is that as long as the scale of Hawking radiation is very well separated by the UV scale, you don't see in the spectrum of Hawking radiation a big effect due to the UV Lorentz breaking. And so you see the problem with analog gravity is not so much that we saw it then in experiments, because we have learned how to look for Hawking radiation by looking at correlation in density-density pairs. And recently it was shown convincingly that there is in black holes made with a waterfall trick in Bose-Einstein condensate, a region where you see a spectrum of phonons exactly with the structure of correlation corresponding to a thermal bath at the Hawking temperature. But you see, the point is that not so much that we have seen it in Bose-Einstein condensate, which is important, but also that we have finally understood that this Transplanting problem, which was a standing problem in gravity, is not there as long as the scale of the Hawking radiation is different from the scale of quantum gravity. So we don't have to worry about the UV completion of quantum gravity provided by quantum gravity as long as there is this separation of scale. So we learn general lessons even if we look at a particular case.
Can I ask a question here?
Yes.
Stefano? So in the case of fluids, of course, we know that fundamentally there is a discreteness and so on, and the continuum description is no longer valid. Where is that? So you're saying that scale, as long as there's a separation from that scale, you don't face this Transplanting problem? Is that?
Basically, the result of the Hawking radiation, the thermal bath at the Hawking temperature set by the surface gravity of the black hole, is robust in the sense that you don't have deviation or important deviation from thermality as long as there is this separation of scale. It's basically irrelevant, the UV completion, if it happens at energy very different from the energy of the Hawking radiation. In spite of the fact that the derivation seems to rely on the completion of the UV completion of space-time, because it seems to rely on the fact that space-time is continuum, even if you trace back these modes close to the horizon.
Okay, thanks.
So lesson 2, can we do more? And well, before we do more, I need to be sure that we are on the same page. I will need to use some diagrams, and I want to be sure that everybody follow it. If you are in relativity, you have basically several ways to go to infinity. One is infinity in time, one is infinity in space, but then you have infinity in the direction of light, which is future light-like or null infinity. And then you have the corresponding definition for past light infinity, past time infinity, past space. But space infinity is only one, not past, of course. Now, what we can do normally is if we want to represent this infinity in a finite distance, there is a trick by which you can do a transformation of your metric that preserve the structure, the causal structure. That means doesn't change the structure of the light cones that is so important, for example, when you want to characterize black hole. And so you can bring this infinity at a finite distance. And so, for example, Minkowski will look like this. So you have the light-like infinity is a kind of finite distance plot in this diagram. And then you have time infinity and space infinity. And then you have a constant time slices and constant space slices, okay? Now, if you have a star sitting here will be something that the matter will always be time-like, and so it leaves and start from past time-like infinity and some future time-like infinity. But if you form a black hole, basically you draw the fact that at some point a region of your space-time cannot be reached outside. There are light rays that cannot reach the future null infinity, but they end up in the singularity. So you cut here basically a line here and you close your diagram. And that is what you call the singularity. Okay, so this is the diagram corresponding to a collapse into a black hole. Now, what happens? It happens that if you put this together with the idea that there is Hawking radiation, you are in trouble with quantum mechanics. So imagine I built a pure state, a pure quantum state on one slice of my space-time here. And then I evolve this quantum state. Of course, if there is no evaporation, everything is fine because the singularity you see is a kind of boundary. But until I reach the boundary, everything is fine. But now if I have instead a collapse diagram, so imagine there is the star here forming the black hole. Now they form a singularity, but then I completely evaporate the black hole in a thermal bath. I'm in trouble because you see, I can define a pure state on this surface, but then here I get basically a thermal bath, which is a mixed state. And you see, there is no way you can have a unitary evolution from the surface sigma 1 to the surface sigma 2. But unitary evolution is a tenet of quantum mechanics. So it looks like the black hole evaporation, the fact that there is this singularity is basically taking away quantum information, that the evolution cannot be a unitary evolution, and so that there is a problem between quantum gravity and unitary evolution in quantum mechanics. Now, the interesting point is that you can have the same problem in analog gravity. So you see, you say, how can I have the same problem in analog gravity? Well, basically, I told you that space-time in analog gravity is where there is a well-defined hydrodynamic approximation. So what you can do is that you can create a system where, for example, at the center of the drain hole, the hydrodynamic approximation fails. And if I do so in a way that doesn't kick out atoms, so that the atoms, for example, in the Bose-Einstein condensate are conserved, it looks like I'm reproducing a loss of information, because basically what is happening is that the Hawking partner will fall in this non-hydrodynamic region and basically be lost to me. I have to trace over them. And so a quantum pure state, which is the state formed by the Hawking pairs, which being produced by the vacuum is a special kind of state that, for those of you that know this, is called the squeeze state. Basically still a pure state, is still a unitary evolution. But once I have to trace on the Hawking partner that are falling in the analog singularity, then I will get only a thermal bath, and I'm back to square one. Basically, I have a thermal bath here. But how that can this be? You see, a Bose-Einstein condensate, for example, is a pure quantum system, and if I don't lose atoms, there is no way information can be lost. The problem, what it is clear that the problem is that we are describing the system not at the level of the atoms. We are describing the system at the level of an emergent metric that we treat classically, plus quantum excitation. Can we do better than that? Well, there is a way to characterize a condensation, which is not the Bogoliubov approximation, where you say that I have a classical wave function of the condensate in quantum excitation. But what I can do is basically I can characterize the condensation by two-point correlation function. And this two-point correlation function can be diagonalized in a formalism which is called the formalism of natural orbitals, that was introduced by Penrose and Oesinger in 1954. Basically, this is a formalism that allows you to track to not lose the fact that you have also atoms forming the condensate. There are objects that are atoms in the condensate phase that in principle can be excited to the excited state, right? So basically you will have now a condensate phase, and you have a creation and destruction operator that are taking atoms out of the condensate phase and promoting them to the excited phase. So why we adopted this formalism? Because in this formalism, what you can do is that you can keep track of the quantum nature of what you call the spacetime. Before we were the spacetime for us was basically the classical wave function of the condensate, and we were describing the propagation of quantum excitation over it. Now we are taking into account that this spacetime is made of atoms, and there is a number of atoms, N0, that are constantly forming the condensate phase. You can show, is a lengthy job, but you can show that you can recast the analog gravity formalism in this analog gravity framework within this formalism. And then what we did is the following. Given that Hawking radiation is very difficult to analyze, we analyze as a first exercise cosmological particle creation. So we consider a space-time where you expand for a finite amount of time, and then you look at, before you don't have any quasi-particle, any phonons traveling on the space-time, you're in the ground state, you expand, and then you look at what you have created. This is a classical exercise, but we did it taking into account the atoms in the condensate and using a further refinement of the formalism that allows you to be sure that at each step, the number of atoms is always conserved. There are no, the total number of atoms, condensate and excitation is always constant. So if you do so, what you get is that you basically see that there is particle creation. And what you realize is that this particle creation is basically produced by taking atoms out of the condensate and put them in the excited phase. This generates a mode, more excited mode that you call the particles that have been created by the expansion. So quasi-particle creation basically remove atoms from the condensate, so reduce N0 and increase Ni, which are the possible, and I are the possible excitation of the levels of the excited atoms. Now, what is the consequence of this? Is that if you look at the operator that describe the evolution from the initial vacuum to the final state, this is a squeezing operator. That means an operator that is a unitary operator. And so there is no information loss. However, and is a very, and that is intuitively what you would expect and what normally expect. But now this squeezing operator acts on the whole Hilbert space of the atoms in the condensate and the excited one. The C operator, ladder operators, are including basically the condensate operator H0 and H0 dagger, basically the stuff that is destroying and creating atoms in the condensate. So you see that how the particle creation happens also from a microscopic point of view. And the interesting point is that you see that there are correlators that are suppressed in the number of the atoms in the condensate, in N0. So what is happening is that if you have a whole universe where this is happening, these correlators between the atoms in the condensate and the particle created are negligible because N0 is very large. If you have a black hole, N0 should be associated to the atoms that are forming the black hole region. And if the black hole shrinks, these correlators, which are suppressing 1 over N0, are becoming more and more important because N0 becomes smaller and smaller. So what you get, the picture that you get is that even if you generate your initial state in a state where you basically have the vacuum of the phonons, of the quasi-particle, and your mean field. So you factorize your state in such a way that your Hilbert space, you write it as Hilbert space of gravity that I consider, I forget because I take the metric as a classical object, times the Hilbert space of quantum matter. Then what is happening, you see in the out phase, it doesn't factorize anymore. You cannot factorize this as atoms in the condensate factorization with quasi-particle created. You have correlators which are non-zero. And then what is happening is that when you meet the analog of a singularity, you have necessarily to do a trace, and you lose the Hawking partner. And if you don't, if you're not able to describe the singularity for what it is, a region where you have the atoms, you don't have the hydrodynamic limit, then you are lost. So you see, the lessons that is teaching you in this case is this, that the information loss problem in Hawking radiation is basically a semi-classical gravity problem. It comes from the fact that when you take the Hawking partner and they fall into the black hole, you want the Hawking partner, you cannot describe them anymore once they touch the singularity, because they become part of the substratum. But you have no control on the atoms of space-time in this formalism, in semi-classical gravity. So what you do, you trace on the Hawking partner, and then you are left with a mixed state. If you instead describe the evaporation, taking into account the atoms of space-time, then the operator that acts on the whole Hilbert space is always a unitary operator. And this unitary operator tells you that there is no information loss. Simply, once the black hole is evaporated, you don't get a classical Minkowski space and a thermal bath. You get a very highly entangled state between the atoms of space-time that are forming what you call Minkowski space and the Hawking quanta that have reached infinity. That is the... Sorry?
So can I just ask a question at this point, which is, so if they're highly entangled, is there any sense in which you can, post the evaporation of the black hole, talk about a condensate with excitations anymore? I mean, the separation of the Hilbert space, the fact that you're factorizing it, in which case it would appear very, I mean, we really don't know what the role of primordial black holes are, or any tiny black holes in our universe, but it suggests that you go from a sort of the semi-classical phase of space-time with these excitations to one which is truly fully quantum, right? And where you can't make the separation, which is sort of a fairly startling conclusion, because you don't, from Hawking radiation giving rise to such a deeply entangled final state, where you can't even extract out the effective classical degrees of freedom.
I think you can, in the sense that the point is that it's not that you can't, let me put it this way, it's an observational problem at that point. The problem is that we don't have instruments so far that can probe the atom of space-time, right? In a Bose-Einstein condensate, you can always open the condensate and look at correlation between atoms instead of phonons. So if you go for the atomic description, we recover anything. But that doesn't forbid you to do another experiment where you look only at phonons correlators. Normally, what we are going to do, imagine you have an experiment where the black hole evaporates. You simply are going to average out this. You basically replace, you are not able to do an experiment that is at the Planck. At least we are not able at the moment to do experiments that are probing these quantum atoms, the atoms of space-time. So basically, you will be forced to see this the space-time as a classical object, and then simply you will throw this correlation away. It's the difference between a true loss of information and the fact that information is practically not recoverable, because practically there is no way you're going to reconstruct all these correlators with the atoms of space-time, because you need somehow some device which is able to go beyond the classical space-time structure, and whatever we have is not, right? You don't have the instruments to measure these correlators, basically.
Okay, so you're saying that effectively it will continue to be, I mean, there's nothing that prevents it from actually having, this effective or this classical piece along with some complicated quantum fluctuations, which that separation is not ruled out, is what you're saying.
No, exactly, because the correlators are not telling you that you have Planck scale macroscopic fluctuation of space-time, that the space-time is in a quantum regime per se, no? The space-time is always underneath the space-time atoms, whatever they are, right? But the fact that there are correlators between these atoms and what you call the Hawking quanta, which are themselves collection of excited atoms of the fundamental system, right? You see, behind this idea, one has to be careful. There is an assumption that there is a unique Hilbert space that basically, once we will go to quantum gravity will not have only the discrete structure of space-time, but that discrete structure will generate, its Hilbert space will also generate the Hilbert space of matter. That matter and gravity are not two separate entities. You see, if, because you can have another scenario where, you know, the Hilbert space of gravity is always separated from matter. They have completely different origin. They are completely different. But this, there is no quantum gravity proposal that at the end really, I think, proposed this. For sure, not string theory, but also discretization of space-time. The idea is that somehow there will be a way not to see matter as coming from the same discrete structure that generates space-time. Also because in general relativity, in modified theory of gravity, it's so difficult to separate the matter and the gravity sector. It's just a matter of different representation to move. For example, an f of r theories of gravity can be mapped in a scalar tensor theory.
Mm-hmm. Okay.
So the idea is that the space-time you end up with is not a highly fluctuating space-time, but is a space-time which is composed by the Hilbert space, the total Hilbert space, see a unitary evolution. It's only when you are not able to see the substratum because you are not able to perform basically experiments that see the correlation at the Planck scale in this case. Then you basically replace your space-time with a classical object, and of course, then the correlators between these atoms of space-time and the Hawking quanta, all they go to zero, and you have lost information because the Hawking partner have become part of the substratum once they fall in the singularity.
That's useful. Yes.
Okay, so final lessons. I will try, and I realize that this is a bit long. So the final lesson has to do with the cosmic pies, with the fact that we see nowadays that so much of our universe is made of dark energy that we don't know. Of course, the standard model of cosmology is called lambda CDM, where lambda is the cosmological constant. But you see, we have a problem with the cosmological constant, because if you assume the energy of the vacuum, of course, this would be unbounded, because if you consider space-time to be a continuum. But even if you put the cutoff at the Planck scale and you do a quantum field theory calculation in 3+1 dimension, then you get that the energy density goes basically as m Planck to the 4th. Then you see the problem is this is a huge scale, while the scale we see for the cosmological constant is much smaller. Actually, 120 order of magnitude smaller than m to the 4th, so m Planck to the 4th. But you see, in analog gravity, you may have the same problem. If I ask you what is the vacuum energy of the phonon, you would take this energy to be cut off basically by the scale of Lorentz breaking I showed you before, which is, for those of you that are more familiar with Bose-Einstein condensate, is the so-called Illy scale. So this is still a huge cosmological constant. So how you get out of it? Is it really what does matter in an emergent gravity system? Well, this is a very interesting problem, because you see, here you have to take into account that we are not quantizing gravitons. We are not quantizing the metric and talking about gravitons. We are saying that underneath the metric, there is a more fundamental system, a discrete system, a quantum discrete system. So let's get back to the equation that we call the Cauchy-Pitavesky equation, but let's not neglect now the back reaction due basically to the excited state. These are called in the jargon anomalous density and mass, are basically expectation value of 2-point correlation function of the excited state in the Bogoliubov approximation. So this is a non-relativistic equation. So at most we can simulate the Newtonian dynamics if we want to interpret this equation as an equation for the background in a gravitational system. Can we do that? So the first thing is that you want to have, in order to have an analog of Newtonian gravity, something with a mass. And normally phonons are the Goldstone boson of a U1 breaking, so are massless. But if you add a soft U1 breaking term, this is a trick that can be done also experimentally. You can basically give a mass to your quasi-particle. Now, with this quasi-particle with a mass, we want to check if you can recast the dynamics of the background in the form of the Newtonian dynamics for gravity, which is the so-called Poisson equation. The Poisson equation for gravity is, without this 1/L square, is nabla square, the gravitational potential, 4 pi g Newton, the density of the matter, and you can add the cosmological constant if you want. I have added this. This is normally what is associated to a massive graviton and is providing basically Lorentz breaking term. This is the most general Poisson equation. And then object will move under the influence of gravity with Newton's law. Now, can we find, for example, the analog of the Newtonian potential? Yes, you can prove that if you look at density perturbations on your fluid, on your Bose-Einstein superfluid, basically they will act, you look at the Hamiltonian for the quasi-particle, you will see that there is a term that is exactly like the gravitational potential for them. And this term, this gravitational potential, depends on our microscopic system in this way, and macroscopic parameters in this way. You remember lambda was the soft U1 breaking term. Now, once we have the gravitational potential, we can put it back in the initial equation, and we can even separate the effect of the excitation in a part which is present even when there are no phonons, and in a part which is instead generated by real phonons living on the condensate. And what you get, surprise, is exactly a modified Poisson equation, where this is the density of the real phonons. You have a g Newton, which is emergent from the microscopic parameter. It's not a fundamental scale. You have an emergent cosmological constant, which is related to these terms, which are the expectation values of the quantum excitation in the ground state of the phonons, are related basically to what is called in Bose-Einstein condensate, to the depletion. And they have a Lorentz breaking scale, which is related to the Hilly length. So at the end of the day, you can introduce basically energy densities and compare them, and you find out that you have a very tiny energy density for your cosmological constant with respect to the emergent Planck constant, Planck density, which is basically determined by the grade of dilution. This ρ0 a cube is the dilution factor of the condensate, and you want to be much less than 1 in order to adopt the whole Gross-Pitayevsky equation. It means that the density of atoms, the number of atoms in a volume determined by the scattering length, which is the distance at which they typically feel each other, is very small, is a dilute condensate. And note that this cosmological constant, you can also show that is naturally negative. So it would predict a negative, not a positive one like the one we see, and is related to the depletion factor. So it's interesting that you see what is telling you is that this is not the grand canonical energy of the atoms, is not the canonical energy, is really a subset of that energy. It's the amount of atoms which are not in the condensate, which are there even when there are no real phonons, which are giving a constant back reaction on the condensate, which for you is your space-time, and they are entering in the dynamic of the condensate exactly like a cosmological constant. But in order to find this cosmological constant, you cannot adopt an idea like quantum field theory. You see, we were getting a large number adopting the quantum field theory idea. While here, what we are discovering is that in an emergent gravity scenario, you have to look at the analog of the Einstein equation to see what gravitates. And only then you see what is really the energy of the vacuum. By the way, you can do this also for a relativistic BC, where the atoms are a relativistic bunch. And in that case, in some corner of parameter, you can recover Nostrom gravity, which is basically a scalar theory of gravity. You see the field equation for Nostrom gravity, these are called the Einstein-Fokker equation, are resembling very much the Einstein equation, but with the Ricci scalar instead of the Einstein tensor, and the trace of the stress energy tensor instead of the full stress energy tensor. And in this case, you have a positive cosmological constant. So you can even get closer to general relativity. You will never get general relativity because this is a scalar system. So at most you can get scalar gravity. You have the system where there is a container, there is the fundamental, for example, in the case of relativistic atoms, the fundamental Minkowski space. So you cannot get a full background independence like in the Einstein gate. You need to go to a different set of ideas. For example, there are ideas in group field theory, which is a candidate theory for quantum gravity, for implementing the same kind of condensate scenario, but in a system which doesn't have a priori the breakdown of different variants. So closing up, so we have seen 3 lessons. One is that Hawking radiation is robust with respect to the UV modification of spacetime, as long as there is a separation of scale. Lesson 2 is that the information loss problem in black hole, when it's seen from the point of view of analog gravity, is not a problem. You know that in analog gravity, there cannot be information loss. The problem appears to be that you need to resort to a description of the evaporation process where you can track down the Hilbert space of the quantum degrees of freedom inside the space-time, and the correlators, the subtle correlators which are generated between these quantum degrees of freedom of space-time and Hawking quanta are necessary in order to keep track of the quantum state purity and to get a final result which is not in agreement with quantum mechanics. Lesson 3 is that the cosmological constant problem may be a problem in a setting where you have that gravity is emergent, of recovering the Einstein field equation. Only once you recover the Einstein field equation from your emergent gravity system, you will be able to see what gravitates. And then only then you can determine what is the cosmological constant. You cannot determine the cosmological constant, apply quantum field theory on a curved space-time and cutting off at the supposed discreteness scale, because you will basically not keep into account what is exactly the source of gravitation in your emergent gravitational equation. Many other problems in principle can be addressed because, for example, one can try to localize how the Hawking radiation emerges. Where is it produced very close to the horizon? Is it produced farther away? Is there a quantum atmosphere, for example? There are works that have been done in this direction, for example, by Binot and Fabry recently. And so I hope that I just convey to you that analog gravity are not just a system, where you can provide experiments where you can test ideas of quantum field theory and curved space-time. That is all nice and very interesting, given especially that phenomena like Hawking radiation, it will be very hard to see them in nature in astrophysical black hole. Nonetheless, there is more than we can learn. We can learn from analog gravity how, in a framework or in a scenarios of emergent gravity where there is a different substratum with respect to what we call the metric and the gravitons, how some open issues in gravitation theory can be seen, and this can guide us toward possibly even a way to test these ideas in gravitational settings. Thank you.
Thank you, Stefano. Let's virtually everyone claps. So we can open up the session for questions if there are any. Just unmute yourselves. We've already asked quite a few questions while the talk was going on. This is sort of the RRI way of doing things. We just interrupt the speaker and keep on asking questions. So, are there? Yes. So Sam has a question. Supurna says, thanks for the very interesting talk. And are there any other questions that people have?
May I ask one question?
Yeah, sure, yes. Please.
In standard model, if you think of the Higgs field as forming the condensate, how far we will have to push this Higgs field? Or my main question is that in the standard model, there is already a kind of BEC there. Can that be pushed a bit far to get some of the features that you have described?
So you're asking if we can have an analog model of the standard model?
Yes, exactly. Or maybe from the standard model itself, driving on
you can generate the gravity.
Yes, exactly.
Something like induced gravity a la Sakharov, you mean? Something where you use an analog gravity, but okay, I would say this, what I find, I mean, I don't know for sure the answer to your question. I never investigate something like this, but let me tell you one concern I would have in starting a program like this. You see, the standard model is basically written in Minkowski space, right? Normally, what we do is standard model in Minkowski space. So in that case, you will have the same problem I just told you from step one. That means that you write your, then if you use the standard model as an analog system, you will inherit basically the structure of the container and the fixed structure, the causal structure of Minkowski. So what is going to happen is that you will not recover fully a theory which is background independent. The only way, well, there is a conjecture, however, that a setting an analog gravity may generate something which is background independent if you have the microcausality notion between the fundamental fields living in the fundamental Minkowski spacetime, the container, and the emergent fields is different. But then you see you have a problem, because then you cannot use in the fundamental container the standard model that we know, because that is already what we measure. So it seems to me that it is much more fruitful in case to follow another idea, which is if you want to go in this direction, to go in a sense, there is this approach which is called group field theory, which is basically kind of second quantization, where you in the manifold is a group manifold, so it's not real spacetime. And when you create and destroy quanta of spacetime, and then you can look at the quantization, the condensation in this quantum field theory, and then that would give rise to spacetime. They've tried, for example, to generate a post-Big Bang universe in this setting. Then you get rid of the problem that you have a free spacetime, a fundamental structure which is already a spacetime in which to do your quantum field theory to start with. That may be a way to try to make the analog gravity scenario into really a quantum gravity scenario.
I see. Okay.
Let me add, however, that if you have a discrete model of space-time like causal set, the continuous limit of causal set is somehow, once you have to recover also the geometrodynamics. So also there, in a sense, that is an example to me of emergent gravity at the end of the day. And there, for example, they don't have Lorentz breaking, but you do have to insert a scale which appear in non-locality at the level of the emergent equation, for example, in matter. But I guess that there could be, some kind of non-local extension to general relativity also as a possible byproduct with suppressed terms that are difficult to see, but they may be there and could provide a signature, Lorentz invariant signature, but still a signature.
Okay. Yeah, thank you.
Thanks, Stefano. Are there any other questions? Okay, there's somebody else in the chat.
There is a question in the chat.
Yeah.
Is there some mechanism which this does not trickle down to a low energy by renormalization group argument? This is a very good question. It is a question that is called the naturalness problems in Lorentz breaking scenario. And yes, normally what is happening is that if I write down a dispersion relation like the Bogolyubov one, the one with a k to the fourth over some m Planck square, even if you start with a theory that way, radiative correction, if you have many particles, will trickle the Lorentz breaking down to the dimension 4 operator. So what you are going to have is that you're going to have in the dispersion relation that omega square equals c square p square. The c square becomes different for different particles. And that is bad, of course, because we have very severe constraint on low energy Lorentz violation. There are several ideas to protect the low energy sector. One is that you have an improved renormalization group, because it was proved that the renormalization group drives toward Lorentz invariant in the infrared for this theory, but it does so too slowly, logarithmically. So there is an improved idea by Sibiriakov and collaborators where they have basically that there is a very fast running at the Planck scale, and basically below the Planck scale, you have already Lorentz invariant in the low energy part. Another idea is that you have Lorentz breaking all in the gravitational sector. You have a theory like Corella gravity or Einstein-Eder gravity. And then the fact that G Newton is so small tells you that this Lorentz breaking trickle toward the, and they have, no, the other point is that you need to have a Lorentz breaking scale, which is different from the Planck scale. So G Newton, the Planck scale, and the Lorentz breaking scale are very well separated in the gravitational sector. Then when you couple to matter, radiative correction by gravitons will induce Lorentz breaking to the matter, but what is happening is that it's suppressed basically by the scale of Lorentz breaking divided by the Planck scale that is coming from G Newton, square at least. So what is happening is that in this case, is if the Lorentz breaking scale in gravity is way lower than the Planck scale, you are protecting the matter sector, which is the one on which we have the stronger constraint. You may say that we have constraint also in gravity because we have seen gravitational waves, but the gravitational waves we have seen are very low energy. So this UV Lorentz breaking would be very difficult to see. Basically, it's invisible. We have to resort to other kind of phenomenology, not gravitational waves as we see them, in order to see this Lorentz breaking in the gravitational sector.
Sam, do you want to, is there anything that you want to ask? Okay. All right. So I'm curious about this. I'm not sure I fully understood the cosmological constant, quote unquote, resolution, or this new way of understanding it. It kind of went by a bit fast, but is the idea somehow that you talked about somehow that there's a classical component to this, gravitating component to it? And I don't, I
yeah,
mean,
well, look,
yeah.
the idea is very simple. Okay, let's go through the idea. Basically, you take the equation describing the background. So this is the equation for the classical wave function of the condensate. It's really from what is here is encoded the classical background of the condensate. It's the one over which the quantum object, the quasi-particle propagates. And this is the back reaction of this of the object on the background. So we can say, can we say this, that this is some sort of a Poisson equation where you can rewrite it as basically the part for the background provide you with a Newtonian potential, because you have a metric and can extract a Newtonian potential if you like, and then you have that the quasi-particle provide the source of gravity, and you may have a cosmological constant. The answer is yes. What we do is that we understand the perturbation, what they feel as a gravitational potential. Then we insert the gravitational potential in this equation, and basically we separate now a part which is the real phonons, quasi-particle contribution, from the contribution that you have also in the vacuum of the quasi-particle. So this is the vacuum energy, if you like. And you can recast it exactly in this way. The derivative in time goes away because you are in the Newtonian limit. Everything varies very slowly. So you are reminded with the repulsion. You have this Lorentz breaking contribution because, of course, you have the Hilly length, and then you have that the phonons act as a source of, as this usual energy density of matter, and these parts instead, which are there even when there are no real phonons, provide you with a cosmological constant. And you realize that what you call G Newton is an emergent quantity dependent on the fundamental parameters of the condensate. Similarly, the cosmological constant has a prefactor and is dependent, as I was saying, on these vacuum expectation values. So what is telling you is telling you that you can describe the dynamics of the condensate as a gravitational dynamics for an effective gravitational potential sourced by the quasi-particle, exactly like in Newtonian gravity, and by a cosmological constant, which is small, naturally small. But you see, it's because G Newton is emergent to be very small. And basically, this is telling you that, and what is related to this cosmological constant is related to the fact that there is no perfect condensation. You cannot have all the atoms in the condensate. There are always excited atoms, because basically the two vacua are inequivalent. There is a Bogoliubov transformation. So the vacuum for the phonons is not the vacuum for the atoms. The atoms are also in the excited state. And what is happening, this cloud of excited atoms are back reacting on the condensate and give you a constant of scale that you call cosmological constant. And this is something that you would not have predicted just by quantum field theory arguments. So the quantum field theory argument fails because it fails to predict what gravitates in the emergent system. That's the lesson. That basically cannot be computed as the total zero point energy of the condensed matter system, even when taking into account the natural cutoff coming from the knowledge of the macrophysics.
Okay. Thank you. So I don't think there are any other questions. Thanks for an extremely interesting talk, at least for those of us who are familiar with this. And I hope somewhere people sort of working in experiments have some, will take back some message from this, which is that quantum gravity, which is in some ways so distant from experimental reach, is being realized in these very realistic models, in analog models. And I think that that's a very interesting, hopefully there'll be, would at least de-exoticize, if you like, ideas of black holes and so on. So Sanjeev, would you like to, yes? Yeah,
thank you, Stefano, for the talk. Yeah, enjoyed it actually.
Yeah, so thank you so much, and let's thank Stefano again for a very nice.
Thank you.
And hopefully we'll see you in RRI one of these days.
Yes, hopefully so.
Okay.
Have a nice day.
Yes, you too.
Thank you. Yeah. Okay.
Bye.
Bye.
Thanks,
Yeah.
Stefano.
Bye. Yeah.
See you.
So
Bye.
I'm going to end the session now. Yeah. Thank you very much.